Did you know that time moves faster on the moon than on Earth? It's a mind-bending concept, but it's true. This fascinating phenomenon is due to the principles of Einstein's theory of general relativity. While the difference is incredibly small, it's significant enough to be measurable with our atomic clocks. This difference in the flow of time has profound implications for our understanding of the universe and our exploration of space. Imagine two identical clocks, one on Earth and one on the moon. Over time, the clock on the moon will tick slightly faster than the clock on Earth. This difference, while seemingly insignificant, highlights the incredible power of gravity to warp the fabric of space-time. Albert Einstein, in his groundbreaking theory of general relativity, proposed that gravity is not a force, but rather a curvature in the fabric of space-time. This revolutionary idea changed our understanding of the universe and how it operates. This curvature is caused by the presence of mass and energy. The more massive an object, the greater the curvature it creates in space-time. This means that everything from stars to planets and even smaller objects can warp the fabric of space-time around them. Imagine space-time as a stretched sheet. When you place an object on this sheet, it causes a distortion, much like how a heavy object would create a dip on a stretched fabric. If you place a bowling ball on the sheet, it will create a dip. This dip is analogous to the curvature in space-time caused by a massive object. This dip represents the curvature caused by the bowling ball's mass. The larger the mass, the deeper and more pronounced the curvature. Similarly, massive objects like planets and stars create curves in space-time. These curves are what we perceive as the gravitational pull. Einstein realized that this curvature not only affects the path of objects but also influences the flow of time. Objects moving through this curved space-time experience changes in their trajectory and speed. The stronger the gravitational field, the slower time moves. This phenomenon, known as gravitational time dilation, means that time passes differently depending on the strength of the gravitational field. This mind-boggling concept is one of the most important discoveries in modern physics. It has profound implications for our understanding of the universe, from the behavior of black holes to the expansion of the cosmos. Einstein's theory continues to be a cornerstone of modern science, influencing everything from GPS technology to our quest to understand the very fabric of reality. The Earth, being more massive than the Moon, has a stronger gravitational field. This stronger gravity means that time flows slightly slower on Earth than it does on the Moon. It's like being at the bottom of a swimming pool where the water pressure is higher. Think of it this way: time is like a river, flowing at different speeds depending on the surrounding terrain. Near massive objects, the river of time flows slower due to the stronger gravitational pull. This difference in time flow isn't just a theoretical concept, it has been experimentally verified. Atomic clocks, the most accurate timekeeping devices ever created, have shown that time indeed moves slower at lower altitudes, closer to Earth's gravitational field. Section 4. Space travel and time implications for missions. The difference in time flow between Earth and the Moon has practical implications for space exploration. For example, GPS satellites, which orbit Earth at high altitudes, need to account for this time difference to provide accurate location information. Imagine a GPS satellite sending signals to Earth. Because time moves slightly faster for the satellite, its clock would run slightly ahead of clocks on Earth. Without accounting for this difference, GPS systems would be inaccurate by several miles. As we venture further into space, understanding these time discrepancies will become increasingly important. Future missions to Mars and beyond will require even more precise timekeeping to ensure safe and successful exploration. Section 5. A lunar time zone, keeping track on the Moon. As we establish a more permanent presence on the Moon, the need for a standardized lunar time zone becomes increasingly important. Currently, lunar missions operate on time zones based on their country of origin. Imagine multiple lunar bases, each operating on a different time zone. Coordinating communication and missions would be incredibly complex and challenging. A unified lunar time zone would streamline operations and enhance overall efficiency. Establishing a lunar time zone is not as simple as it sounds. Factors such as the Moon's rotation and its elliptical orbit around Earth need to be considered. However, the benefits of a standardized timekeeping system for lunar exploration are undeniable and significant. Section 6. The future of timekeeping, Beyond Earth. The moon's faster clock is just the tip of the iceberg when it comes to the mysteries of time in the universe. The moon's unique gravitational field causes time to pass slightly faster than on Earth, a phenomenon that has intrigued scientists for decades. As we explore further into the cosmos, we are likely to encounter even more extreme gravitational environments where time behaves in unexpected ways. For instance, on planets orbiting close to massive stars, the intense gravitational pull can significantly alter the flow of time, making a single hour on the planet equivalent to several years on Earth. Imagine black holes, regions of spacetime where gravity is so strong that nothing, not even light, can escape. These cosmic giants warp the fabric of spacetime to such an extent that time itself is stretched and distorted. Near a black hole, time would slow to a crawl, practically stopping altogether from the perspective of an outside observer. This phenomenon, known as time dilation, has been a subject of fascination and study since it was first predicted by Einstein's theory of general relativity. These extreme environments provide fertile ground for testing the limits of our understanding of physics. Scientists and researchers are continually developing new technologies and methods to study these distant and often hostile regions of space. By studying how time behaves in these unusual circumstances, we can gain deeper insights into the fundamental nature of the universe. Understanding time in these contexts not only helps us grasp the complexities of the cosmos, but also paves the way for future space exploration and potential human settlement beyond Earth. Section 7. Conclusion. Time and the final frontier. Time, an ever-present yet elusive dimension, has always fascinated humanity. It is the thread that weaves the fabric of our existence, and nowhere is its complexity more evident than in the vast expanse of space. The discovery that time moves faster on the moon than on Earth is a testament to the mind-boggling nature of our universe. This phenomenon, known as time dilation, challenges our perceptions and invites us to delve deeper into the mysteries of the cosmos. Einstein's theory of general relativity, once considered a radical idea, has been proven time and again through scientific observation. His groundbreaking work has provided us with a framework to understand how time and space are intertwined, bending and stretching under the influence of gravity. As we continue to explore the cosmos, understanding the intricacies of time and gravity will be crucial to our success. The more we learn, the more we realize how little we know, and this drives our quest for knowledge and discovery. From navigating spacecraft to communicating across vast interstellar distances, mastering time is essential for unlocking the secrets of the universe. Precise timekeeping allows us to synchronize missions, calculate trajectories, and ensure the safety of our astronauts. The exploration of space is not just about pushing the boundaries of technology, it's about expanding our understanding of the fundamental laws that govern our existence. Each mission, each discovery, brings us one step closer to unraveling the mysteries of time and space. And in this grand cosmic dance, time plays a leading role. It is the silent conductor of the universe, orchestrating the movements of celestial bodies and the flow of events. As we venture further into the final frontier, we carry with us the hope that one day we will fully comprehend the nature of time itself.